Concepts. Concepts allow us to categorize our world and make sense out of what we see, hear, feel, and experience. But this is not the case with a machine, so how can you start talking to your model in the same language? Exactly this you'll find in our recent paper. So what's the problem? Generally, we treat our model as a black box. For a given input, it produces some output. But what we really want is to have a set of explanations for the obtained prediction, also called transparent model. And this issue is tackled by the field of interpretable machine learning, where the methods categorized in two main branches: post hoc methods that explain model prediction on inference time, and self-explaining models that gradually learn how to explain themselves. One of the recent advances in this field is called concept bottleneck models, where the concept stands for the meaningful, coherent, important, and independent high-level representation comprehensible for a human. The idea behind the concept bottleneck models is to use concept as an intermediate step. Firstly, feature extractor, or CNN, predicts whether the concept is present on the image or not, and then this binary set of values is used to perform the task. But the issue arises that the concepts are selected and annotated manually. Annotation is quite a laborious task, and also the concept set that was produced by a human might not possess enough predictive power. In our paper, we propose a cross-modal conceptualization in bottleneck models, or in short XCB models, that adopts more moderate assumption and instead uses text descriptions to construct concept set, transfer domain knowledge, to reinforce disentangled and human interpretable latent representations. And I'll walk you through architecture just in a second. So, standard computer vision model consists of feature extractor that produces some latent representation, followed by predictor that solves the task. XCB model treats concept as a discrete latent variables, so we use Gumbel sigmoid to make latent factors binary. On training time, XCB also uses textual part of a similar structure, so we have some feature extractor, we have the predictor, we have the latent representation, but modality is different, text. Textual model, or concept extractor as we call it, favors concept corresponding to text span. So we introduce several modifications to NLP model to satisfy this requirement. I'll show this modification just in a minute. At this point, concept extractor produces latent variables which are interpretable in textual format. So the additional agreement propagates it to the visual part, meaning that the textual model guides concept inside of our framework. For a given sample, we want our extractor to identify informative textual spans that could be used as a concept. And the structure of the model itself ensures the interpretability at the level of dataset, meaning that spans with a similar semantic might be encoded in the same latent factor. Our model can be thought of a shallow transformer with each head corresponding to a particular concept. We also use ideas from slot attention, for example, normalization across concept rather than tokens, and disentanglement, for example, ensuring sparsity through end marks and diversification regularizer. In our evaluation, we want to test that text makes concept interpretable and at the same time improves robustness. And we can achieve this without substantial sacrificing in domain performance. And for evaluation, we used three datasets: synthetic dataset of shapes, less synthetic dataset of birds, and realistic dataset of medical images. And each data point consists of 4 parts: visual and textual modalities, set of attributes, and label. We measured the performance using F1 score. To measure interpretability, we adopt DCI score, or disentanglement, completeness, and informativeness, that measures how well the latent representation resembles the underlying factors of generative process, or attributes. This metric proposed by Eastwood and Williams. Also, we use survey on quality of interpretations and did use X-score metric. Moreover, we introduced a non-robust feature in our dataset and measured the performance and interpretability. Then we performed case study using integrated gradients to see the attribution to non-robust feature. XCBs achieve comparable to CBMs with annotation performance, but does not require explicit concept in annotations. Also, XCBs achieve a highest DCI and X-score, so the latent representation is more interpretable there. Also, our framework allows us to extract explanation in such a form. So we have image, we have the prediction, and also we have set of concepts that were activated the most. Finally, XCBs performs better than the standard model in terms of robustness. For a sample with a non-robust feature that is located in the upper left corner, the standard model attributes mostly to this shortcut, whereas XCB attributes to the shape itself, to the robust feature. Thank you for your attention. Please check our preprint using this QR code. And if you will be in conference in person, please visit our poster. See you soon.